in chapters 1 through 8, we've sort of been using a point particle model of everything. We want to know where something is and how fast it's going. But we've been neglecting the fact that objects have some sort of size and shape to them. That's translational motion. What's happening for chapters 9 and 10 is that we're starting to think about extended bodies, or rigid bodies as they're called. They're not just points, and when you act on something with a force, you have to think about where that force is being applied. We're still going to be talking about something's momentum and energy, but that'll mostly be for the center of mass. And then there's also a possibility of rotation around the center of mass, for example. And one of the new things we have is called torque. Kind of like force, but it has different units, but it's instead of getting something moving in a translational sense, what you're doing is you're using torque to get something turning. And then this chapter 9 in particular is talking about usually, rotation is that things can spin or roll, and a rigid body which is not spinning or rolling will have balanced forces and balanced torques. So here's two people that are standing, and somehow there's gravity which is pulling them wanting to rotate both ways, but if the torques all cancel, then they don't fall down. And then I got some questions this morning in the pre-class survey about what's the pivot point. So I think the best way to think of the pivot point is to think of it as being an axis of rotation. You've got, like a door, for example, has hinges on it. We call the hinge sort of the pivot. So something can turn around a hinge. So when an object can turn around some rotation axis, we say it's got rotational motion, and sometimes called a pivot. And if you think about these forces, how do you open a door? They show three different possible forces you can apply. F1 is you push on the hinge. You kind of probably know from your intuition that that's not going to really open the door. But F2, or in this case, close the door. If you want to close the door, you would push F2. You would not push F1. So another way of putting that is if you applied the same force, magnitude, at either the hinge or way over at the doorknob, you'll be able to rotate the door much more effectively if you push on the doorknob. And so the reason there is that you're pushing at a farther distance from the axis of rotation, and that gives you more torque. And then there's more than one way to push on the doorknob. You can push kind of in, the way you want to rotate it, F2, or you could do the wrong thing, F3, where you're pushing a different direction. So you can imagine the same magnitude force, but pushing kind of in the door, trying to squeeze the door. Squeezing the door is not going to turn the door. So once again, we would say F3 has less torque around that axis of rotation than F2. There are three things that matter here when you're trying to cause rotation. It's the place where the force is exerted, the magnitude of the force still matters, and also the direction of the force. So you can imagine F3 and F2 there might be the same magnitude force, might be applied at the same place on the door, but the direction there matters as well. Do you remember when I talked about work? I talked about the dot product, or sometimes called the scalar product. So this is not torque. Work, I said the fun fact here is that it's the dot product of force and displacement. When you're multiplying two vectors, there's different ways of multiplying two vectors. You can either put a dot or you can put an x, and they mean completely different things. So this is dot product. F dot D, for example, is the work, and work is scalar. So this is a new thing called the cross product. It's a different way of multiplying two vectors. And the fun fact of the day is that torque is the cross product of two vectors. One of them is the vector from the pivot point to the place where the force is applied, cross the force. So it looks like this. So we call that first vector r. It's just a distance, and it's going from wherever your pivot is out to where you're applying the force, and then cross that force itself. And we'll kind of compare these two. They have different equations, and what's can be a little confusing is that work actually and torque do have the same units, but they're completely different concepts. It's just a coincidence, really, that they have the same units, I think. So work, for example, is a scalar, F dot D. It could be negative, I guess, but it doesn't have any kind of directional sense to it at all. But torque does have a direction. There's a little n hat there, But what we're going to be doing in this chapter and the next one is mostly thinking about torque as being kind of clockwise or counterclockwise. That I think of as being a direction, and you can put a plus for counterclockwise and a negative for clockwise. Another big difference here is that work is maximum when the two vectors of the displacement and the force are in the same direction, whereas torque is maximum when they're in perpendicular directions. And torque is actually zero if the two vectors are parallel. And it's because if you look at the equations for scalar product, you see this cos theta. So there, if theta is 0, then cos is a maximum. Cos of theta of 0 is 1. But here you have a sine theta for torque. And so if theta is 0, so your r vector and your f vector are in the same direction, you end up with 0. And then sine has a maximum at 90 degrees. So when sine theta is 1, that's when the force is perpendicular to the vector r from the pivot point to the point where the force is applied. So the equation your book gives is just the magnitude equation, rf sine theta. So they use the Greek letter tau to denote torque. R is the distance from the pivot point to the point where the force is applied. F is the magnitude of that force. And theta is the angle between the force and the vector, r. And then the units are newtons times meters. And then another really good thing the book does is it talks about something called perpendicular lever arm. So if you have, for example, some vector r, and you've got maybe some force F or something like that, and this is the pivot, then what you can do is you can draw a dashed line through the force, which is called like the force line. It's a line. And then what you can do is find the shortest distance from the pivot to that force line. And that is a thing called r perpendicular. And it is, it's the lever arm, perpendicular lever arm. And it turns out that I think there's if you think of this as being theta here, then this is theta. So this r perpendicular sine theta, I guess, is equal to r perpendicular divided by r. So r perpendicular equals r sine theta. So this is the real definition of torque. But if you define this as being r sine theta and rearrange this, you find that the torque is just equal to the perpendicular lever arm times the force. And so if you can do a good sketch of your forces and find the perpendicular lever arm right from your sketch, you can save yourself the trouble of multiplying by sine theta. And you can just find r perpendicular. It's a nice little trick, and we're going to use it a lot. It would have worked really well if you had done the pre-class survey. Some of you did this morning. You hold a meter stick steady with the same mass suspended at the opposite end. Rank the magnitude of the torque you need to apply in each situation to keep the stick steady. So what you're doing is you're applying some kind of torque like this to counter the gravity torque of these masses pulling down. And what's important here is going to be, since the force line is vertical in all these cases, then what matters is this distance. This is r perpendicular A. This is r perpendicular B, way out here. And this, from here to here, will be r perpendicular C. And so what I was thinking here is that torque is just going to be r perpendicular times the force. It's the same force in all three cases because it's the same mass, but what matters is the horizontal distance between that force line and the pivot point. Another way of putting it, another question, why is it better to put the handle on the opposite side of the hinges? So this is a nice little symmetric door that someone has invented where they put the doorknob right in the middle. So as a physicist, I find this a little offensive. You don't do that, okay? You put it as far as you can away from the hinge. So force causes things to accelerate along a line. Torque is kind of the rotational and analog of torque. It causes things to have angular acceleration. as opposed to linear acceleration. So you want to get something rotating. Torque is force times this perpendicular lever arm, and lever arm is the distance between where you apply the force, I guess it's the perpendicular distance, between where you apply the force and the hinge or the pivot point. So you're putting the handle further from the hinge, increases that perpendicular lever arm, and therefore it increases your torque for the same given force. So this is what's called a torque wrench. So you can use this if you want to, I guess, turn something. I think they use this for spark plugs a lot when you're installing a spark plug in a car. They want you to tighten it to a very specific torque. And so as you're tightening this, this dial shows you, it actually shows you foot-pounds here. But that can also be converted into Newton times meter. So a foot is a unit of distance, and a pound is a unit of force. So they call foot-pounds. Anyway, then we have all these little bolts, and I can screw in this bolt so tight. I don't know if you've ever overscrewed something where you can't loosen it. Well, it may be difficult to actually loosen it, but if you're smart, you can get a bigger wrench. Pick out one that's something like that. And you can't really see it even in this, but I can apply the same exact force, loosen it very, very easily with a longer lever arm for the same bolt. Because what matters to tighten or to loosen this is going to be the torque that you apply. So if you can only apply a certain amount of force, you can really increase that torque by increasing that lever arm. And then I guess the other thing I was going to talk about is this is sort of a way of showing exactly what was in that pre-class survey, is that you can pick up a mass and think about how much, torque it takes to keep it from rotating. So if I were to put it right straight up and down, like that, then it no longer takes any torque to hold it from rotating. In fact, it wants to rotate the opposite way. Okay? But it gets more and more the sort of farther it gets away. The other way of actually reducing that is to pick one of these other closer hooks. Actually, it doesn't take much at all to keep it from rotating there. But you put it way out here, you really have to apply a lot of torque at this sort of yellow handle to keep it from rotating down. And we'll get back to gravity torque a little later. So, Lewis uses a 20 centimeter long wrench to turn a nut. The wrench handle is tilted 30 degrees above the horizontal, and Lewis pulls it straight down with a force of 100 newtons. So what I'm going to do is to try to sketch this. Again, it's really important to draw a little diagram, so do a sketch. So you can kind of draw what you're trying to do here. The wrench handle is tilted at 30 degrees above the horizontal. So I'm going to try to draw a wrench, and Lewis pulls straight down in the end, so the force that he applies is here. Calculate the torque. It also says 20 centimeters long, so I think from here to here is this 0.20 meters from here to here. So that's sort of my diagram, and the question is, what is the torque? So what I'm going to do, I guess I could do another sketch. I could do what's called an extended free body diagram of the wrench plus the... And what that looks like is this. So what's interesting about... So in a free body diagram, I was always drawing a point, and then the forces acting on that point. For an extended free body diagram, you still want to think about the forces, but you also need to think about the torque. And so you usually draw like a rectangle or a circle or something kind of bigger, and then you put the forces where they are applied. So there's a force here. There will probably be some other force that's actually probably being applied here. But the point is that this is the pivot. So when you draw an extended free body diagram, you should put a rotation axis somewhere. And the rotation axis, in this case, is coming out of the page because it's going to rotate in the plane of the page. And so when a rotation axis comes out of the page, you just draw a dot, and it's called the pivot point. But this is that force. And you're just asked to find the torque. So what we're going to do is define counterclockwise This is what the book does. And then what you have to do is think, if this is the pivot point over here, and this is the force that Lewis is applying, which way would that force want to rotate the object, which is the wrench plus the nut? And so I kind of think that if you think of it going a little like that, that's the way it wants to push it. So that's opposite the way the clock turns, counterclockwise. So this is a positive torque. So I would say that torque is equal to F times R perpendicular. And I would say that here's a little triangle. Here's R perpendicular. Here's your 30 degrees. And here's R. So this is, strangely enough, cosine, I guess. Cosine of 30 degrees is equal to R perpendicular over R. So this is why it's really important to draw a diagram for these things, because this 30 degrees, it's not actually the angle between your R vector and your F vector. I think 60 is probably that one. So we're going to use cosine instead of sine here, but that's okay. We end up with torque is equal to F times R times cosine 30. So it's 100 newtons times 0.2 meters times cosine 30 degrees, and I get the torque is equal to 17 newtons times meters, and I'm going to put a plus sign, positive, because the torque. So I would use the same numbers if he was pulling up or something, but then I would get a negative torque because it's trying to cause a clockwise rotation. So let's go over the sign conventions for torque that's being used in this book. Basic idea is if you are if the torque you're applying wants to cause something to rotate clockwise around its pivot point, we call it a negative torque. And if the torque you're applying wants to make it rotate counterclockwise, we call that a positive torque. So different forces applied at different places can be either positive, can give either a positive or negative torque, or a zero torque if it doesn't cause any rotation at all. That's if the force line passes through the pivot point. So a couple questions from this morning. What time is it? A few more minutes. How is rotation different from circular motion? I think the idea here is that circular motion, as we've been doing it in the past, is when something that's modeled as a point particle travels on a circular path. So you've got a centripetal force going towards the center of that circular path. What rotation is when you've got an object which now has a shape and it can rotate around something. And so you might even have, like, here's the center of mass of something. It can rotate around that center of mass. And things, if you toss something now, it could have both. It could have the center of mass giving some motion and some rotation about that center of mass. So this is kind of a new concept, and it requires you to think about torque. I think the concept was termed rigid body equilibrium when I was taught in high school. Is that the same thing, or is it slightly different? I think it's the exact same thing. So if you've learned about that, I call it static equilibrium, but it's all the same. And the pivot point, so I think, once again, a better name for the pivot point is rotation axis, because it's always a line in real life. But often when we draw it on a piece of paper, the rotation is happening in the plane of that paper, and so that line comes straight out of the paper, and that's why it looks like a point. And so your textbook calls it the pivot point. But just keep in mind that it's a line. Where is the gravitational force exerted on a rigid body? So this is weight. When calculating the torque due to gravity, you may treat the object as if all its mass were concentrated at the center of mass. So really, gravity is reaching out and pulling on each part of every single little molecule in this hammer is being pulled downwards by the force of gravity. But if you add up the torques of all the, I guess, particles, then you can treat it as if gravity is coming out and just hooking on the center of mass and pulling straight down there. Which is why, if if I find the center of mass and support the hammer from right below it, then the gravitational torque is passing right through the pivot point, which is my finger, and so it produces no torque. If I put it here, then gravity will give it a torque and rotate it that way, or if I put it here, it'll rotate it the other way. So the center of mass is sometimes called center of gravity because that's where we can think of gravity as providing a torque. The idea with static equilibrium problems is that you draw the extended free body diagram that shows where each force acts on the object, you set up your xy axes, you put a pivot point, and then you have three equations. The sum of all the forces in the x direction is 0, the sum of all the forces in the y direction is 0, and the sum of all the torques, which can be positive or negative, have to also be 0. In equilibrium, an object has no net force and no net torque. So all the external forces have to sum in their x direction to be 0, y direction to be 0, and all the torques, external torques, have to be 0. So what you do is you draw an extended free body diagram, typo there, sorry, that shows where each force goes on the object. Don't forget to define your axes, choose a pivot point, and there's this suggestion that they should be done to simplify your calculations, but it shouldn't. More than one choice will get you the right answer, so don't worry too much about it. And the equations are F net x equals 0, F net y equals 0, and the net torque equals 0. So do you want to do some examples? Oh, yeah, the other thing that you should just know is that the gravitational torque, when calculating the torque due to gravity, you can treat the object as if gravity is pulling on the center of mass, or sometimes called the center of gravity, CG. So that's labeled right there. So in reality, I guess, gravity pulls on every single molecule in the object, and so it's going to have an infinite number of torques, but they'll all be infinitesimal. But when you integrate and sum up all of those torques due to gravity, you get the same answer as if you had taken the gravity as if it was just like coming up with a hook or something and pulling down on the center of mass. So it's a little mathematical trick we use so we don't have to integrate. So example, and often these objects are uniform, meaning the center of mass is at the geometric center of the object, and that's what's going on with the ladder leaning against the wall. It says uniform ladder leans against frictionless wall. What is the minimum coefficient of static friction between the floor and the ladder to prevent it from slipping? So, okay, well I can actually draw some of these forces right on here. So I might draw like the normal force here. The problem is that there's also another normal force up here. So there's the floor, so the normal force from the floor acts upwards, the normal force from a wall actually acts sideways. Right? Normal just means perpendicular to the surface. I guess you could even get a normal force from the ceiling, which points down. Right? So we're going to have to distinguish here because they're different. So let's call this 1 and 2. So maybe this is point 1 and point 2. So we're just going to draw our diagram here. Okay, so let's also define plus y to be up, plus x to be towards the right. I'll just mention here that point 1, we'll call that the base, and we'll call point 2 as the top of the ladder. Okay. The wall is frictionless. Says in the question. So what that means is that if there's any F static at point 2, it equals 0. But I guess maybe if the wall is sort of pushing to the right, probably this might want to slip out to the right. So I think there's a static friction force actually to the left here, Fs, at point 1. But we can even start doing this. The F net, say, for example, in the y direction, is going to be equal to 0. So what are all the forces? Oh, no, let's not forget. Gravity pulling down. Normal force on the bottom, static friction on the bottom, normal force on the top. There's no static friction on the top because it's frictionless, and then the gravity pulling down. So I think that's all the forces. 1, 2, 3, 4. So if I'm not missing any, then some of these are 0, so they don't have any x component, like the static friction and the normal force 2. So I think just normal force 1 is pointing up, and then minus mg. And so you can actually figure out that n1 equals mg, just from this. Call this maybe equation 1. The other thing we're going to do is F net in the x direction is equal to 0. Oops. 0. So that's going to be, there's a plus n2 is acting in plus x direction, and then minus the fs1. So what that means is that n2 equals fs1. So I guess that's another equation. Call that equation 2. And then lastly, the torque. So you can't do the torques until you define a pivot, right? So let's define point 2 is the pivot. Because I guess there's 2 forces there, so it'll get rid of 2 of the torques. And we'll also say that counterclockwise is plus. And when you define this way, the torque from N1 is going to be equal to 0, and the torque for F static friction 1 is equal to 0. Basically, the idea is wherever you choose the pivot, any forces that act on the pivot point will have 0 torque. Because I guess their lever arm is 0. And even actually if the force is on a line, the force line passes through the pivot point, you also get 0 torque there. So when you do your net torque, well actually I'm going to have to figure out some of these lever arms here, so let's draw it. Here's the wall. Here's mg. So that's the force line for mg. So I think if you do this distance right here, this is r perpendicular for the gravity. And don't forget that this whole distance from the wall over here is 1.5 meters, right? So it's going to be half that, I think, if the ladder's uniform. And then the other thing is that this is N2, so a little force line going like this. You do a perpendicular down to the pivot point, and you get R perpendicular for N2. And that actually is equal to this distance, which is labeled, it's 2 meters, right? So I would just say that from this diagram, R perpendicular of N2 is equal to 2 meters, and R perpendicular for the gravity is equal to 1.5 meters, but divided by 2, because it's halfway, so 0.75 meters. And also, from this diagram, you have to think about the direction. So you've got the torque due to gravity, and you've got the torque due to N2. Torque due to gravity is, it wants to pull it down, so rotating about that bottom thing, that's counterclockwise, so it's positive. Counterclockwise. So it's positive. And the torque from N2 is pushing to the right, so if the pivot is fixed, it's going to rotate it clockwise. So is clockwise, so that's negative. So when I write this equation, torque net is equal to 0, it's going to be the torque of N2, like the vector there, plus the torque due to gravity, which is a vector, that's going to be negative N2 R perpendicular N2 plus mg times R perpendicular g. Does that show up? Yeah. So that's going to give you another equation. Shift this over. You can solve that out. You get, we know the numbers, so it's 2, N2 is equal to mg times 0.75. So you get N2 here is equal to 0.75 divided by 2 times m times g. So that's sort of like a third equation. And then also you can actually right now combine. You have two equations for N2. If you combine equation 2 and equation 3 here. You can say that n2 equals n2, so you get fs1 equals 0.75 over 2 times m times g. And remember, we are looking for the coefficient of static friction for mu sub s, and it says something about minimum coefficient of static friction. So to me, you're talking about static friction, you're asked for the coefficient of static friction, it means your object is just about to slip. So when the ladder is just about to slip. So that's the only time you can use that equation for static friction. You use the static friction max to slip. So you've got that Fs1 is equal to Fs1 max, which is equal to mu sub s times n1. But actually we have n1 somewhere, right? Yeah, it was mg. So recall from equation 1 that we derived, n1 equals mg. So what that means is that Fs1 is equal to mu sub s times m times g. So we're going to plug this into the above. Running out of room again. So you get mu sub s times m times g equals 0.75 over 2 times m times g. So this is one of the reasons I like to keep things symbolically, is that look at all the things that cancel. You can divide both sides by m, and you can divide both sides by g. And it just magically all works out. Mu sub s is 0.75 divided by 2. Probably meters over meters if you kept everything in SI units. Anyways, it's 0.375. So there's your answer. I would say that also any coefficient of static friction that's greater than this would still keep the ladder in equilibrium, right? So it's a minimum. Less than that, then it would slip out, and you wouldn't be able to lean the ladder like that above. And this is before anyone's even climbed on it. So I would say this is the minimum use of S.
I was wondering, why is n2 not 0 if it goes through the pivot point? And why is n1 0 if it doesn't go through the pivot point? If that, like, so the axis.
N1 and N2 are both non-zero normal forces, but the torque from those forces is 0 if the force line goes through the pivot you've chosen, right?
Wait, what? Sorry, what pivot point did we choose, 1 or 2?
I chose 2 to be the pivot, the bottom of the ladder. So that means N2 and oh no, I didn't, sorry, the bottom of the ladder was 1, right? So point 1 was the pivot.
Oh,
Did I
okay.
mess that up?
You wrote 2, I think.
Okay, that's good. So you guys
Okay.
can do that. So that's wrong. So sorry. So let's just do, you guys are paying better attention. Point 1 is the pivot. Therefore, yeah, that didn't make any sense. So sorry. Any guidance on where to generally put the pivot point? Besides putting it in the place that simplifies the problem, is there any general rule or advice about where to put the pivot point? So I do have some comments. First, actually, a piece of advice is that sometimes, especially when you get to chapter 10, the object's actually rotating. And then sometimes it just could rotate, like it's a door on a hinge or something. And in that case, it's just best to put the pivot where the thing's really rotating. Like an axle on a wheel or something, just put the pivot at the axle. But in static equilibrium problems, nothing's moving. Nothing actually is rotating, so the rule is it doesn't matter where you put the pivot, the net torque around any pivot is 0. So it's your choice. But I would say maybe pick a point where there's more than one force acting on it that you don't care about, because the thing is, when you set up the torque equation, all of the forces that act on the pivot will have 0 torques. So they're not going to show up in your equations, so you're not going to be able to solve for any of those. Right? Here is an idea where I've drawn, maybe it's a bowl or something, and so there's a marble at the bottom of a bowl, and it's just sitting there. You can also turn the bowl upside down and put the marble, balance it right on the top of the bowl. So in both of those cases, it's in equilibrium. It doesn't move. Or you can have just a marble on a flat surface. So the question is, what happens when you give the marble a little bump of delta V? Well, in that case, if it moves over here, there'll be a restoring force. Restoring force, which points it back towards equilibrium. So, and in fact, this is partly due to the fact that the potential energy, gravitational potential energy, has increased a little bit, and it wants to go back and seek its lowest potential energy. So what actually ends up happening is that it oscillates back and forth. Oscillation around equilibrium is what happens. We'll talk more about that when we get into oscillations and sound effects. So this is called stable. But what happens if you perturb this one by a little delta V, then what will happen is that the force will actually take it away. So this is an accelerating force. Instead of slowing it down, you get the ball accelerates away from equilibrium. So it rushes away, and that's called unstable. So they were both in equilibrium, but one's stable equilibrium, one's unstable equilibrium, and then there's something here, which is you give it a little delta V, you get no acceleration. I guess it would still move away, but it's what's called neutrally stable. Neutrally stable, I guess. Perturb it a little bit, but it doesn't rush away. And I guess the idea here is that if the center of gravity is, and you take is in an object, and you draw a line straight down, and it falls inside the base of an object, then it's in stable equilibrium. It's going to balance. If you perturb it a little bit, it wants to fall back to its original position. And if it falls outside the base, it's not only unstable, it's probably not in equilibrium either. It's going to have a torque which takes it away. Maybe a better way of putting it is, if a slight disturbance from equilibrium results in forces and torques that restore it to equilibrium, that's stable. So the cone on its base is stable. However, the cone on its tip is unstable. Anytime you put a little bit now, it's going to have an acceleration away from equilibrium. John has brought an empty bottle of champagne, not from last night. This is an old one. So what you can do with this one is you can actually set it up so that the center of mass of the whole system is right over the base. Like that. So, whoop. So you have to have it in a little bit more. John is better at doing this stuff than I am. There you go. So it's sort of unstable, but the center of mass is pretty much right over the base, and so it doesn't fall. If you have a piece of wood, for example, and I give it a little perturbation, it also wants to kind of oscillate and fall back to its equilibrium positions. This is sort of stable. Unless you tip it too much and it falls over. You can make it kind of more stable because if it's sitting like this, now it requires more of an angle, quite a lot of angle to actually get it to rotate away from its equilibrium. So we talk about almost how stable an object is after it's stable by how much of a tipping angle does it need to get it to topple over. So this is an example which comes up quite a lot. A uniform box of width W and height H is tipped onto its bottom left edge as shown. What is the maximum angle theta for which the box, when released, does not tip all the way over onto its side? So what we're going to do is assume that the center of gravity is at the geometric center. So this was not true for those weirdly loaded trucks. But for a uniform box, you'd imagine that halfway up the height and halfway along the width, right in the center of it, is where you're going to find the center of gravity. And then we can define this as the pivot. Okay, and then what we're going to do is we're going to say that the maximum value of theta will be when the torques are 0, right? The torque due to gravity is 0. Torque due to gravity equals 0. And what that means is that the r perpendicular for gravity is 0. So what this means is that the force line from gravity passes through the pivot. So you passes through the pivot. And you didn't really have any choice to draw the pivot anywhere else than this place where it's going to rotate around. So right like that. So you just have to find theta for that. So this is all about drawing a diagram. And I guess you guys are experts at drawing diagrams now from all these many chapters, but I'll show you how I would draw it. So here's the box, and here is the floor, and here is the theta, and here is this line which goes up to, I would say, this point. I guess we can draw a couple, here's a right angle, I guess. This is the h over 2. And this distance right here, from here to here, is the w over 2. Can you kind of see that? And then this angle, I'm kind of running out of space here, but this angle from here to here, this is a vertical line, and this is the horizontal line, so I think that this angle is 90 minus theta. And then the sum of interior angles in a triangle have to add up to 180. You've already got a 90 degree, so I think that means that this up here is theta. So I can redraw that triangle now to look like this. There's a right angle down here. There's theta up here. And this is h over 2, and this is w over 2. So we can use that tan of theta is the opposite over adjacent, a little SOHCAHTOA thing. So tan theta is equal to w over 2 divided by h over 2. So the 2's cancel. This is a w. And we can just cross out, I guess, times top and bottom by 2. And you get that theta is tan to the minus 1 of w divided by h. So that's a nice one. You can even pop it on your H sheet if you want. But it's a uniform box. How far can you tip it over? For like a refrigerator or something like that before it goes all the way. And you can imagine that even for this piece of wood or something. There's some angle which you can find from its height and from its width where you go beyond that, it falls. Yeah, so, and they kind of talk about this a bit in your book. They don't actually refer to this equation, but this is exactly the equation that they're referring to when you get to this person. They say that if your base of the support is narrow and you're standing upright, you are kind of less stable than if you crouch down and put your base of support farther away. So it's again, you're comparing W, your width, to your height, dividing those numbers, and then tan to the minus 1. You get a bigger angle if you spread out your base of support and reduce your center of gravity. But maybe a better way of phrasing this is which are better, dogs or humans? So you could do this like a dog has a height and a width, maybe, I don't know, some sort of estimate like that. You could also do a human, I don't know, and a width, maybe 1.8 meters. Let's see what my sort of stance is here. If I'm just standing like this, what does that say, 35 centimeters, something like that. So you can do the tipping angle of the puppy and you get about 39 degrees before he tips over. It's tan to the minus 1 of the width divided by the height. That's assuming the puppy is a rectangle, uniform rectangle. So maybe that's a little off. But I guess it would really be the center of gravity of that puppy would be the height, and the width would be I guess still the distance between the outer supports of the puppy. For the human, you just use different numbers, you get 11 degrees. I mean, doesn't this guy just look unstable? He does to me. Okay. Had to throw in some kind of joke. All right. I don't quite understand the types of equilibrium. Does it mean that how objects react after the force and torque being applied tell its type of equilibrium? So the idea is this. Equilibrium simply means that the net force and the net torque on an object are zero. So it's not going to accelerate. But within that thing of, category of all things in equilibrium, there are subcategories based on stability. And there's things like, and so that's, if you give it a little bump, then what's going to happen? So you can have stable, unstable, neutrally stable. There's also something called metastable. Another person asked, it's hard to distinguish between neutral equilibrium and static or unstable. She checked online and found out the potential energy is often considered. And that's absolutely true. That hill and like the upside down bowl and the bottom bowl, if you think about what's happening to the marble, in each case, if it goes up, it's increasing its potential energy. If it goes down, it's decreasing its potential energy. So really, that's a potential energy curve. And so you talk about metastability, even this piece of wood, if you give it a little bump, it's stable. But if you give it more of a bump, it finds a new center of gravity, where now it's even more stable. So, and it could be a ball that's resting on a little slope there. It could go up over a little barrier and then find a better, like more stable situation in situation 3, if you give it enough of a bump. And a bowling pin or even a piece of wood like that, it's got a little bit of stability, but unless it's bumped too much. And isomers are like this. So isomer is a molecule, 2 different molecules that have the exact same chemical formula, but they have different configurations. So normally a molecule is always at its ground state. It's where it wants to rest at. But there can be a different ground state that has a higher energy. And then if you bump it, it can find a better ground state. So, and there can be many ground states if you plot potential energy versus all the different configurations. Well, if you were asked what's the tension in the cable, then what you could do is you'll have to define a pivot, I guess, and try to work out the torques. So I'm going to draw it again here as sort of an extended free body diagram. Here's your tension. Here's this force, M, workbench. So now he's called M2 for some reason. Times G, eating lunch at distance D from the building. So, and then there's the beam is uniform, so there's this distance L over 2 from here to here, which gives you M1 times G, the distance to where the gravity force grabs on the beam, and then there's distance D from here to here, which gives you that. And then there's some like unknown force, I'll call it force question mark, on this pivot. So this is the pivot, which we did talk about. We actually split it up and just solved it. But right now what I care about is that the net torque is equal to 0. And so then you have to think about, if I'm going to put positive being counterclockwise, then the tension is going to provide a positive torque, and these two masses will provide negative torques. So it's going to be, I guess, negative L over 2 M1G, that's the torque from the beam itself, and then minus D times M2 times G. And then to find the torque from the tension, you're going to have to find the perpendicular lever arm. So I'm going to redraw this triangle here. This is tension. So there's a force line which goes through that tension, and here's the pivot over here. You need to find the perpendicular, the sort of shortest distance between the force line and that pivot. So I would draw that actually right about here. You're drawing a perpendicular line to the force line, which goes through the pivot. That's what you're trying to find. And this is what we call R perp, I guess, for the tension, right? So, and then here's your 30 degrees. So again, so I would use, and what else do we know here? We know the distance, right, L. So we know the distance L from the pivot to where the tension is applied. So this is an actual triangle where we would say L is now the hypotenuse because it's opposite this right angle. So I'd say that sine of 30 degrees is equal to this R perpendicular lever arm divided by L. And so this lever arm is equal to L times sine times 30. So all of this stuff is going to go into this positive R perpendicular T. L over 2 times M1G plus DMG is equal to L sine 30. And then similar to this Fx x component, we found that before, which is F net in the x direction is equal to 0. It's just equal to Fx, I guess, minus T cos theta. In a simple machine, so there's no power source, for example, a person provides some input force, Fi, over some distance di. So the I here stands for input. And then the machine provides an output force, Fo, over some distance do. And there's lots of examples of these. And then mechanical advantage is defined as the output force divided by the input force. Okay. So, and you can have a variety of mechanical advantage values. So, example is this crowbar. You've got a, I guess, I don't know if you can kind of picture this, but it's a bar, and you're pushing down on this part. There's a pivot here, and then as you push this down, this goes up. So this kind of rotates that way, this kind of rotates this way, and it pulls the nail up out of the wood. What you end up doing is you push over a larger input distance than the nail moves upward. And I guess also what's an interesting thing to note here is that you do push with less force than the nail experiences. So the nail experiences greater force, so that's part of it. But also, I think it's easier to push something down than it is to pull something up because you can use your own weight to kind of help you do it. So it's another advantage here. But the mechanical advantage is greater than 1. So that's one example. We'll talk more about that in a minute. From the pre-class survey, we talked about actually just using a ramp. So if you use a ramp that has some distance, d input is equal to 5 meters, and you push a cart up the ramp to get maybe into the back of a truck or something, and so there's you could have just lifted it up 3 meters, because that's the total distance that you went up. So what is the mechanical advantage of using this ramp? Here's your angle theta or something. Well, if you use mechanical advantage is equal to the output force divided by the input force, then you could say, well, I guess we have to look at this cart and think of the free body diagram. We've got the mg acting down, and we've got this. This would be your kind of input force acting up like that. And if you define plus x to be in this direction and plus y to be in this direction, that's y, then I think that what you get is that at constant velocity, if you were to push this cart up the ramp at a constant velocity, then the F net in the x direction is equal to 0, which is equal to Fi minus mg sine theta. And so Fi here is equal to mg sine theta, and that's equal to mg times, I guess, the opposite over the hypotenuse of this triangle. But if you think about it, the opposite over the hypotenuse for this triangle is actually Fi is equal to mg times 3/5. And then Fo is pushing the cart straight up. So if you don't use the ramp and you just try to lift the cart into the back of the truck, then Fo is going to be mg, push it to lift something at a constant velocity. So anyway, the mechanical advantage ends up being mg divided by mg 3/5. And so you end up with 5 over 3, which is about 1.667, which a lot of you kind of figured that out. But what's kind of interesting here is that it's also the ratio of the input distance, 5, divided by the kind of output distance, 3. So it's another way of thinking of a mechanical advantage. Yeah, question?
Can we think of this in terms of work done?
Great question. I was just about to think about that, actually. The crowbar shown has dimensions, etc., etc. You press down 50 newtons over a small distance. What is the work input by you, and what is the work output by you? So you can do work is equal to input force times input distance, 50 newtons multiplied times 2 centimeters. So maybe 0.02. Don't forget to convert to meters, right? Meters. To get it into joules, get 1.0 joules. The work output is equal to the output force times the output distance. You get 500 newtons times 2 millimeters, that's 0.02 meters. Again, you get the same number, 1.0 joules. So basically, work out equals work in. This is conservation of energy. And this is a pretty universal principle for simple machines. Totally predicted my slides, huh? Simple machines do not create energy. That's why they're called simple machines. There's no battery inside it, and there's no engine or something. Due to conservation of energy, there's actually a less than or equal to sign. An ideal, frictionless, simple machine with no inefficiencies would produce, as we calculated there, work out equals work in. But in real life, heat is usually produced by internal friction in the simple machine, so the output work is usually somewhat less than the input work. But the work is force times distance, so if a simple machine has a mechanical advantage greater than 1 to reduce to increase the output force compared to the input force, then it also increases the distance you have to push. So that's why there's these two different equations. So that's really good. Here's a simple machine actually with mechanical advantage equals 1, is if you were pulled down in this string, you could pull up. So here's a pulley which is attached to the ceiling. You can lift something up by pulling down on the pulley. So all this does is just change the direction of the force. And we had this in practical as well. We had pulleys that are just fixed and a string goes over it. The purpose of the pulleys is to change the direction of the force. But I think that it's easier to pull down on a rope and kind of use your weight than it is to lift something up. So you might use this in this case. Here's another one, and John has set this up. If you look at the free body diagram, you can see that when the tension in the rope is T, then the upward force on this hanging mass, there's 2 ropes, so whenever you go around pulley, it doesn't change the tension, right? So there's only 1 rope, I guess, but it's going to provide an upward force of tension and another upward force of tension. So the net force on this entire system down here is going to be, 2 tensions up and then the weight down. But you can also try to think about how far you would have to pull this string. So here's point 1, point 2, point 3, point 4, and point 5. The string goes through these distances. If you pull this string a distance x or something at 5, then what that'll do is reduce the length of this string by x, because that's conservation of string. But this distance from here to here, if this is the distance d, then this string has a length of 2d. And so if you've reduced 2d by x, then you reduce this distance by x over 2. What you've got is a 1 kilogram mass hanging down here and a half a kilogram mass hanging up here. And as I pull this one down some distance, you can see they're actually almost in equilibrium, even though they're completely different masses by a factor of 2. But I pull this down some distance, from 7 up to, 17. So there's like 10 inches, but it only goes up 5 inches on that side. So the distance output is half as much, but I'm able to lift it with half as much force. So you can see, and so by using a complicated arrangement of pulleys, you can really increase your mechanical advantage. And then we have this one, in which there are, oh my God, there's 1, 2, 3 pulleys times 3, so 9, plus another 9. There's 18 pulleys, and this string is wrapped around, I don't know how you wrap this thing, but John has wrapped this thing around and around and around, so that when I pull this down, all these little things going around so many times that, it's 18? Is that? So I can, you're lifting 1 kilogram, and if I use my spring scale to measure how much force that's taking to lift this 1 kilogram upwards, oh, it fell off. Now I got a bunch of friction because it easily falls off. Okay, so now I can pull it up, and I'm providing input force of about almost 1 Newton. So actually it looks like more like 0.8 Newtons to lift 1 kilogram. So that's like 10 Newtons on this side. So 10 Newtons on this side, and I'm putting in maybe 0.8 Newtons on this side. So that's a system where you can imagine. I think that sometimes people use this in theater or something where they're trying to lift a curtain or some sort of prop or something. You can use a lot of pulleys to reduce that input force. So here is one where the mechanical advantage is 3 instead of 18, okay? You can kind of again see that if you pull the string a distance x, this will lift the mass up a distance x over 3. So the mechanical advantage is di over do, x over a third of x, you get 3. Oh yeah, my bike. That was the other thing. You can have a simple machine for which the mechanical advantage is less than 1. So what that would do is actually reduce the output force. So you have to push harder on your pedals than the force of between the road and your bicycle. So in a low gear, when I push a distance of 10 centimeters down on the pedal of my bicycle, it causes the bicycle to roll forward a distance of 30 centimeters. So the mechanical advantage is only 0.33. So what that means is that the force that I input on the pedal is actually 3 times greater than the force that's output between the bike and the ground. So why would I want to do that? I think the reason is that I want to go faster. Okay, so I push a little bit on here, and it sends me quite a bit. And in fact, I change gears or something to go maybe, I could go down a hill. I change it to reduce the mechanical, or increase the mechanical advantage. So what that will do, it'll get me a lot, not as far, I won't go as fast, but the force I have to push on the pedals to get a certain force on the bike is a lot less. And if I increase the gear, then the distance I go is a lot farther, but the force is a lot less. And so I have to, it's all about the kind of the speed that you want to get there. When you're walking, your feet have to actually move the whole distance that you're going. And so, or running even. And so there's a kind of a maximum speed you can go by moving your legs. If you use the gears on the bike and a low mechanical advantage, you can move your feet a small distance and go a very large distance, which is why biking is faster than running. It's a mechanical disadvantage, I guess, but it gets you there faster. It's more about efficiency. Okay. Last thing here is about muscles and joints. The last section is sort of a biological section talking about how your muscles are always basically rotating and exerting torques to rotate certain bones around certain joints, okay? Where the joint would be the pivot. So, for example, if you hold a ball in your hand, your bicep muscle tenses and pulls up on your forearm in front of the elbow joint. And then you push down in your hand, and there's a tricep muscle which actually pulls out a protrusion of your forearm behind the elbow joint. So this is how you're able to move around as an animal. Here's an example problem which might come up. You hold a 6 kilogram lead ball in your hand with your arm bent as shown 90 degrees. The ball is 35 centimeters away from the elbow joint, and the biceps attached to the forearm 5 centimeters away from the elbow joint. So they're giving you all these distances in the problem. The forearm has a mass of 1.2 kilograms. So that's going to produce a weight right there. And then you've got the 6 kilogram ball over here. So then they give you the center of mass of the forearm. What is the force of the biceps on the forearm? And also the force of the upper arm on the elbow joint. So what you do is you do an extended free body diagram for the forearm there. And think of the weight of the ball as being an external force pushing down, the weight of the forearm itself as being an external force, and then there's some force upward from the bicep and another different force from on the pivot itself. Okay, so this is kind of the extended free body diagram. Some of these are a little weird here, but let me see if I can sort of solve it on this part right here. So what I'll do is draw this. And I will draw, what do we have? We have the weight of the arm. So this is actually, I guess, the weight of the arm. And then we've got the mass of the ball times G. We'll call this W. And then we've got, what else is there? Oh yeah, force upward of the bicep. That's what we're trying to find. And then I would say that the net force in the x direction, which equals 0, all these three forces so far have 0 components. So all forces have 0. We'll define up to be y and to the right to be x components. So whatever force is on this joint here is the pivot. I think that will be, we can just put it like this, F of the upper arm. So that's what we're going to find for part B, is find that force. And for part A, we're going to find the bicep force. But I'm not drawing the pivot force on a diagonal because it's not balancing any other x components. All the x components are 0, so I know it's either straight up or straight down. And I don't know which way, so I'm just going to draw it as up, and if I get a negative number, I'll know it's down. So, F net, the easiest thing to start with, other than torques, I think, is to just do F net y. So it's going to be the force of the force of the upper arm plus the force of the bicep minus the weight of the arm, and then minus the mass of the ball times G. So it's pretty simple. You just get, we'll just leave it like that. And this is equal to 0 by static equilibrium. So for the torque net is equal to 0. It's going to be the torque on the up arm. This one equals 0 because it's at the pivot. Plus, let's see, if this is counterclockwise, an upward force from the bicep will have a counterclockwise torque, so we'll do plus 0.05 times FB, and then minus 0.16 times the weight, and then minus 0.35 times MB times G. So you get 0.05 times the F bicep equals 0.16 times the weight plus 0.35 times MBG. So FB is equal to, it's going to be 0.16 times the 12 newtons plus 0.35 times the 6 kilogram mass times 9.8. And then divided by 0.05. So I get the bicep force is actually 450 newtons. So this is actually another example of a really bad mechanical advantage. It's way less. So your bicep is pulling with a much greater input force than the output force on the 6 kilogram ball. There's like 60 newtons on the ball, but 450 newtons from your bicep. So it's interesting. And then if you want to figure out the force from the upper arm, well, you can just use this equation, right? Now that you know, so the only unknown here, there's two equations, 2 unknowns. You can use this to get F on the upper arm is equal to the weight plus MBG minus FB, right? So force of the upper arm is equal to negative 380. What does that mean? Oh, it's a negative number, so that means that I've drawn it in the wrong direction on my free body diagram. Whenever you do this, so normally when I draw a free body diagram, I know all the directions and I'm always computing the magnitudes of the forces. For the FU, the one that's on the upper arm on the forearm, I didn't know the direction, so I just guessed it. So this means I guessed wrong. Negative value here, magnitude, means F direction is down, which is interesting. So somehow the force of the upper arm is pushing down on that pivot point. I guess because there's so much force from the bicep pulling up to balance those torques. A figure shows a model of a crane that may be mounted on a truck. A rigid uniform horizontal bar of mass M1 is 100 kilograms. So what we're going to do is define our system here that we're going to do the free body diagram of is the horizontal bar. And what we need is to find here is you've got two strings. String A is attached at distance D from the left end of the bar and is connected to the top of the plate. That's what's holding it up from gravity, I guess. And then string B is attached to the floor. So it's kind of being held by two tensions, one up and one down. A little bit like that bathroom mirror. You kind of have to balance these things so that it doesn't rotate. So we need TB, the tension of string B. So what we're going to do is draw an extended free body diagram showing all these things. We also don't care about TA, as it turns out, for this question. So sometimes my intuition tells me maybe I should put the pivot point at where string A is attached there, so that so that the torque from tension A doesn't come into my torque equation, and I don't need it anyways. So so let's define the pivot at point A, I guess, where the string A is attached. So let's draw this. Here's the object. And I'm going to draw, let's use red to draw TB is pulling down there. TA is pulling up here, and we've got the distance, D equals 2 meters from here to here. And then we'll put the pivot there. And then we've got two more forces. We've got this M2G, which is that mass pushing down. It's actually, I think, a normal force, but it's equal to, in magnitude, to M2 times G pushing down. And that is at a distance x. And there's one more force. Do you guys know what it is? I'm missing one force from this diagram. There should be 4. M1G, right? Yeah, so that's the mass. So where do we put it, though? That's the question. Halfway, yeah, L over 2. So it's as if, so really gravity is on the entire beam, but it's we treat the torque from gravity as if it's pulling on the center of mass of the beam, the uniform beam. So, so very good. Let's put it right here, M1G, and we'll call this distance L over 2, I guess. This distance from the pivot is going to be L over 2 minus D, I think, which is really what we're going to need here. So we can now do the torque net equals 0 equals plus TB times D. That's a counterclockwise torque. The gravities are both clockwise, so minus M1G times L over 2 minus D. That's the pivot, that's that lever arm. And then minus M2G times X minus D. Okay, and then there's no torque from string A because it's at the pivot point. So now rearrange to solve for TB. I've got M1 times G, L over 2 minus D, plus M2 times G times X minus D, all divided by D. Again, D is 2 meters here. L over 2 minus D is, I think it turns out to be 0.8 meters. And X minus D, 3.4 meters. So I've got TB, just plugging in all the numbers here, 100 kilograms times 9.8 times 0.8 is that first gravity torque, plus 300 times 9.8 times 3.4 divided by 2, I get 50. 3, 7. Oh, sorry, 50,000. 72. 5 times 10 to the 4. Think? Okay.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.